Welcome back. I tried to do this a few minutes ago and I messed up, so I guess I get to learn too. Anyway, we stopped the last video right about here where we were talking about the first derivative and how when we put test values in the first derivative, that if it's positive, that means the function's increasing. If the test value turns out negative in the first derivative, then the function's decreasing. These, remember, mean imply. So what we had was we had possibly a positive and then a critical value and then a negative. So increasing critical value negative, when that happens, we haven't really checked ours yet, but when that happens, we're going to have a relative maximum. That's called the first derivative test. When we have decreasing and then the critical value and then increasing, it's a relative minimum. Again, first derivative test. So second thing, second derivative. We take the second derivative, set it equal to 0 or undefined. That means do both of them. That gives you what are called inflection values. We've talked about that. And that shows us concavity or shape. So when it's concave up, it looks kind of like this. When it's concave down, it looks kind of like this. Now what we're going to do, I'm going to move the paper a little bit. We are going to look at test values again. I've got inflection value 1. I've got inflection value 2 and inflection value 3, just as examples. When it's positive, when you put a test value in, the second derivative, and you get positive, that implies that you have got concave up. When you put a test value in the second derivative and you get negative, that implies concave down. So that's what I've got written right here. Now the next thing that we're going to do, I'm going to kind of shoot over here and make sure that this fits. So we're going to go through an example. So here's our example. I've got some of it already done, and actually I've got it all done because I tried this before and failed, but that's neither here nor there. But what we're going to do is we're going to look at the function f of x is 1 over x squared plus 2. Now this is not the most exciting function you've ever seen, but it does have some of the elements that we need. So the first thing I'm going to suggest is going back over here to the algebra, we're going to find the zeros. So we set this equal to 0, multiply both sides by the denominator, and you end up getting 0 equals 1, which doesn't happen. Well, you know, we create things, but not that. So there are no x-intercepts. Second thing I'm going to have us look for is the vertical asymptotes. Vertical asymptotes, remember we talked about them up here, didn't really do anything, but they are where the denominator of the function equals 0. And that happens, in this case, if x squared plus 2 is 0. Well, when x squared plus 2 is 0, x squared is negative 2, and that gives us imaginary answers, plus or minus the square root of negative 2. Again, we don't use that in our class, so none. So these are kind of boring, but at least we need to use them and try. So the third thing we're going to do, which is another algebra thing in my view, you can use calculus for it, but I'm going to use algebra. We're going to look for horizontal asymptotes. Now, horizontal asymptotes, in an algebra perspective, use the numerator's degree versus the denominator's degree. And when we do that, we have to label the numerator's degree and the denominator's degree. So I go back up here to my problem. My problem has 1 as the numerator, and so its degree is 0. It has x squared plus 2 as the denominator, and x squared has a degree of 2. So there's that. So then we compare them. Numerator degree versus denominator degree. So if the numerator degree is less than the denominator degree, then we say automatically that y equals 0 is the horizontal asymptote. If the numerator's degree is equal to the denominator's degree, then we find this thing called the ratio of leading coefficients, and that is our horizontal asymptote. ratio of leading coefficients is just the numbers in front of those high-powered terms. Like the denominator has a 1x squared, so its coefficient would be 1. This doesn't apply to our problem. Then the third option is if the numerator degree is greater than the denominator degree, and in that case there is no horizontal asymptote. Sometimes there are different kinds of asymptotes, but not horizontal. So ours has a horizontal asymptote of y equals 0, and that's because the numerator degree is 0, the denominator degree is 2, 0 is less than 2, so automatically we get y equals 0. So that's the algebra information. Now, next thing I want to do is I want to start working on the first derivative. So the first derivative, and it's already done for us, I'm not going to show you the quotient rule and all that because you know how to do that. So I'm going to use the first derivative and kind of use it as simplified as I can. Let me scoot this up. So I've got f prime is negative 2x over the quantity x squared plus 2 squared. Well, we've got to set that equal to 0. And I was kind of messy here, but it is equal to 0 when when 2x is 0, which is when x is 0. So that's our critical value. We also try to find out where it's undefined. Well, the first derivative is undefined if x squared plus 2 is 0, or x squared plus 2 quantity squared is 0, excuse me. And we found up here, trying to find the vertical asymptote, that can't happen. The stuff inside the square is a sum of squares can't equal 0. So just like there was no vertical asymptote from this denominator value, this is very similar. There's no critical value for it. So the only critical value we have is 0. Now, we mark that, get a test value, and I'd love to ask you for your idea of the test value, but this is a one-way conversation today, sorry. Anyway, I chose -1 and I chose +1. If we put -1 in the first derivative, here's first derivative, put -1 in it, we get a positive number. So we get positive 2/9. -2, here's the -2 times +1 is +2, and then this stuff is squared, so it's positive anyway. So we get 2/9, which is positive, and positive is going to go over here, which is going to imply increasing. Then I put +1, and I know I didn't mark that very well, so let me fix it. That f prime of +1. We are going to do that. Oops, I guess you can't see that, can you? I got my hand in the way. All right, well, let me straighten that out. Okay, so here's what we've got. We've got +1 in here. Gives us -2 times +1 over this 1 squared plus 2 squared. So it's -2 from this, and 1 plus 2 is 3, 3 squared is 9, so we get a -2/9. So I'm going to put a negative here. Now, how does that work? Well, a negative or a positive over here implies increasing. A negative here implies decreasing. So it increases and then it decreases. We have a relative maximum at 0. Okay? All right, here's the third attempt at this problem. This page is the one I just turned to a minute ago, and we're going to do step number 5, which I've just numbered 5. It doesn't matter, but it's for the second derivative. The second derivative is already done. It's 6x squared minus 4 over x squared plus 2 to the third, the whole quantity to the third. So we set that equal to 0. We try to make it undefined, and that will give us what are called inflection values. So the numerator is what makes it 0. So 6x squared minus 4 is 0. That gives us 6x squared equals 4. Divide by 6, reduce the fraction, you get x squared as 2/3. That will give you x is either plus or minus the square root of 2/3. Those are inflection values. Then we try the denominator equal to 0 to find out where it's undefined, and that's the same thing we've been trying to work on for the last two parts. It's not a vertical it has no vertical asymptote, it has no critical value from there, and this is not going to be 0 either, so there are none. So I set the inflection values on either side of 0. This is a kind of a little negative number and a little positive number. These are the numbers are like, point something, so I put a test value of -2, put a test value of 0, and a test value of 2, so that I can stay away from the actual values here and here. Put the test values in, get 6 times -2 squared minus 4 over -2 squared plus 2 cubed. That's going to give me 6 times 4, which is 24, minus 4 is 20. I've got, this is -2 squared is 4, plus 2 is 6, 6 cubed. I know that's messy, but 6 cubed. What matters is that I've got a positive number. That means that the graph right there is going to be concave up. So I put a positive there, it's concave up. Then I tried test value of 0. 0 squared in here is 0, times 6 is 0, minus 4. So we get minus 4 on top. 0 squared plus 2, and then cube that, you get 8 on the bottom. 8 doesn't matter, it's positive, so the entire thing is negative, which gives us concave down. And then put 2 in, that's our third critical value. 6 times 2 squared, 6 times 4 is 24, minus 4 is 20. So that's there. And then 2 squared is 4, 4 plus 2 is 6, 6 cubed is positive. Positive over positive is positive. So I've got a concave up area again. Now the coding for that kind of goes with this. If we've got increasing and concave up, it looks like this. I've got Roman numeral 1. Increasing and concave down, I've got Roman numeral 2. Decreasing and concave up, I've got Roman numeral 3. And decreasing and concave down, Roman numeral 4. So I'm going to set up all my important values, my critical value, my inflection values, and I'm going to take the number line, our world, and I'm going to break it up into sections. So from minus infinity to the first one of these, which is minus the square root of 2/3, and then from that to the next important value, which is 0, then from 0 to the square root of 2/3, and then from the square root of 2/3 to infinity. Well, in this region, in fact, all the way to 0, we've got increasing. And then after 0, we've got decreasing. But we've got concave up, concave down, concave down, concave up. I hope you don't hear noises of my house. Anyway, okay, so this looks like number 1 because it's increasing and concave up. This one is increasing and concave down. It looks like Roman numeral 2. This one is decreasing and concave down, so it's Roman numeral 4. And this one's decreasing and concave up, which is Roman numeral 3. Okay, so that's the analysis. You're taking calculus with analytical geometry or analytic geometry, and so we've just analyzed this graph way beyond anything that you can even imagine. So the last thing that we'll do, if you can hang on with me for just a bit, is I'm going to attempt to graph this thing. Okay, now it's not going to be wonderful, but whatever, it's going to be a graph. So I'm going to put some stuff here. We had an original problem, which I've got to look up, of course, because it's on another piece of paper. So it is 1 over x squared plus 2. So our function is f of x is 1 over x squared plus 2. And so there is the original function. And let me try to straighten this thing out. It's not working like I want it to, of course, but we'll see. Anyway, okay, so we've got that. If I put the zeros in, there aren't any. If I put the vertical asymptotes in. There aren't any. If I put the horizontal asymptote, y equals 0. So I'm going to do it this way. So that's the horizontal asymptote. Okay, I'm going to see if I can do this without shaking too much. Okay, then I'm going to put the y-intercept just because I don't have any points yet, so I might as well. So when x is 0, that's 1 over 2, because 0 squared plus 2, so 1 over 2. So I'm going to put that right there, assuming these lines stand for 1 apiece. And then I've got to come back up here and put my values in. So I've got to be increasing and concave up. I need to plot some other points. Okay, so f of minus the square root of 2/3 is going to be 1 over minus the square root of 2/3 squared plus 2. Well, the minus squared is plus, the square root of 2/3 squared is 2/3. So I've got 1 over 2/3 plus 2. So there's your fraction work for the day. 2/3 plus 2 is 8/3. So we've got 1 over 8/3, which is 3/8. Kind of slick. So out here, you know, before you get to 1, somewhere you're going to have a number right about here, a point. And you notice that that matches identically with the other side because the minus disappeared. So I'm going to put plus or minus here and just do them both at the same time. So there are our points. So from negative infinity until I get to this point, I've got to be increasing and concave up. So I'm going to graph it kind of like this. And then I have to turn it into concave down, but still increase. So I'm going to change it to that. And then I'm going to stay concave down, but decrease. And then I'm going to be concave up. So there's the amazing graph that we just analyzed. This extra piece is not really supposed to be there. So there you go. Okay, so there's an example. I know we did this a number of times before spring break, but just a reminder. So I will shut this video off and we'll do something else.